perfectly straight.
Okay. Am I audible? And can everyone see the presentation as well?
Yes.
Good. Uh, so today's topic of discussion is uh, kernel range of a linear transformation and how to associate a matrix with with a linear transformation. Okay. So in last session, we have discussed about linear transformations. We saw the definition of a linear map, uh, and in today's discussion, we will talk about linear transformation associating matrix to it. Okay, so let me first start with recalling a few facts. Uh, so last time, quick recall. So last time we saw linear transformation, the transformation between two vector spaces. So let me recall the definition. So a map F from a vector space B to W is said to be a linear transformation if the first condition was f of v1 plus v2 is equal to f of v1 plus f of v2 for all v1, v2 in V. Second condition was if there is a scalar multiple with a vector, you can take the scalar out and the value will be just function on the vector. For alpha in R and B in V. All right. So this is the definition of a linear transformation or linear map between two vector spaces. And these two conditions are called linearity conditions. Okay. Uh, now there is one more. There is an equivalent condition of proving a linear transformation. You can just it is enough to prove. It is enough to prove that if you want to prove that a map function from B to W is a linear transformation, then it is enough to prove instead of proving both conditions separately, you can just prove this one condition that f of v1 plus alpha v2 is equal to f of v1 plus alpha v2 for some alpha in R and v1 and v2 for all alpha in R and v1 and v2 in V. Okay, so proving that f is a linear transform, it is enough to prove this linearity condition. These two conditions can be uh, proving these two conditions separately is equivalent to proving this single condition. Okay, we also see some example. We also saw some example last time. So let me uh, recall some examples so that you can quickly recall what linear transformation is. So, for example, this map from R to R to R2, and it is defined as f of t equal to t comma 2t. So, is it a linear map or not? Uh, Anyone? So is first one a linear map? First map.
Yes.
Yes, sir.
Ellen. Huh?
Yes.
And what about second one?
No.
Okay.
No, sir.
Yeah. What about third one?
No, sir.
Why?
If
Third one is a linear map, right? Because if you take two vectors, let's say x1, y1, some scalar multiple, and x2, y2, what will you get? You will get x1 plus alpha x2, right? And if you apply separately and take the scalar multiple and this, and then also you will get x1 plus alpha x2. So it is this thing, these two things are equal. LHS is equal to RHS. So it is a linear map, right? So it is a linear map. What about fourth one? Is fourth one a linear map? You just need to check this condition, this single condition. Is fourth one a linear map? Okay, so let's start with the RHS, sorry, LHS. Uh, so again, you take two vectors, all right, and you apply the functions. Function is, so what is, if you take the addition of two vectors, you will get f of x1 plus alpha x2, y1 plus alpha y2, right? And if you apply the function, you will just interchange the value, right? And for the other end, if you apply, if now we are proving RHS. So what is RHS? RHS is this. If you apply this, you will get y1 comma x1 plus alpha times y2 comma x2. And if you add these two vectors, what will you get? 6. It is weak number 6. Is it clear?
yes.
So is it a linear map then?
No.
Yes, it is a linear map. No, we have proved it is a linear map, right? Because what is LHS? LHS is this. What is RHS? RHS is also same.
Okay.
So
Okay.
LHS is equal to RHS. So
Yeah.
it is a linear map, right?
Yes. Yes. Yes.
Right. Uh, okay. So now what next thing we learned last time was the injectivity, surjectivity of a linear transform. Okay. So let me quickly recall that as well. Uh, so injectivity of a linear transformation is again uh, is equivalent to uh, if f of v is 0, then v is a 0 vector. Okay. So I'm always assuming my f is a map from v to w. And surjectivity of a linear transformation is nothing but that the image of F is the whole space W. Okay. So, and if a function satisfied to be both injective and surjective, it is called an isomorphism. Is uh, is a L linear transformation which is injective and surjective. Okay. We also noticed one fact. Basically, I wrote one more fact that if a linear transformation is between V to V or let's say V to W, such that dimension of V is equal to N, which is also equal to the dimension of W, and uh, it is given to be a linear transformation, such that this and such that the dimension is equal to this, then that means F is a linear transformation between same dimensional vector spaces. Okay. Then in that case, um, it is enough to prove injectivity or surjectivity. All right. So isomorphism is equivalent to injectivity, which is equivalent to surjectivity. Okay. So we only need to prove either injectivity or surjectivity, but you need to make sure that the dimension needs to be of the both species the same. We are having a map from the same dimensional space to the same dimensional space. Then only we can talk about isomorphism. We cannot have isomorphism between two different dimensional space, first of all. So in that case, it is enough to prove just injectivity or subjectivity to prove isomorphism. Okay. Now, uh, so in these examples, okay. So let me take these examples from here and paste it over here. So in these examples, let us talk about injectivity, surjectivity, and isomorphism. So which one of those is injective, subjective, or an isomorphism? So what about first one? Is first map an injective map? So how do we prove injectivity? So for injectivity, we need to prove that f of t is 0 if and only if t is 0, right? So what is f of t? F of t is 2t comma t comma 2t. It is 0, which implies that 2t is 0 and t is 0. So it actually implies t is equal to 0. So that means it is an injective map, right? Now what about surjective? Is first one a surjective map? Uh, Answer this is 1 comma 3 belongs to the image of f.
No.
No, right? So it is not a
Surjective.
surjective map,
Yeah.
right? Since it is injective, but it is not surjective, can it be an isomorphism?
No.
It is not an isomorphism because the dimensions are different. It is one dimensional space. Domain is of one dimension and codomain is of two dimensions. So it is not an isomorph. So we need injectivity and surjectivity both in order to prove that it is an isomorph. So it is not an isomorph, right? Now, what about example number two? In example number two, it is not it is not a linear map, so we don't care about it. Now, what about example number three? Is example number three an injective map? Again, we can use the definition. Now, what does it say? It says that x comma y is equal to 0, then x comma y has to be a 0 vector. If and only it has to be a 0 vector. So, what is x comma y? X comma y is, what is f of x comma y? It is equal to x. That is equal to 0. But uh, y need not to be a 0 number. All right. So, in other words, uh, for example, 0 comma 3. What is the image of 0 comma 3? In this example number 3, what is the image of 0 comma 3? It is 0, right? So 0 comma 3, 0 comma 3. So 0 comma 3 is an element. Yeah. So there is a, so 0 comma 3, image of 0 comma 3 is equal to 0. So that means there is a non-zero vector in R2 whose image is equal to 0. So that means it is not an injective map. All right.
Okay.
Now, what about surjectivity? Is it a surjective map? So for surjectivity, you just take any element X in R. So what is the domain? What is the codomain? Codomain is R. So any element of any vector of R is just going to be a real number X, right? Now for any X in R, is there a vector in R2 whose image is going to be that? You can take uh, any X comma 1, let's say. So what is the image of X comma 1? It is just X, right? So for any X. So it is an surjective map. All right. So let me take another example in this. What about is there an element in R2 whose image is equal to 3?
Three comma zero two.
Yes. 3 comma 0 is correct answer. So 3 comma 0, 3 comma 1, 3 comma 2, any number, right? So that is the who. So if I apply f over that, it will be 3. So it is a surjective map. All right. So similarly, if you take any other number here, let's say 4,000, right? So you can just have 4,000 comma 0. So that's what 4,000 comma 0, right? So it will be 4. So it is a surjective map. Now again, is it isomorphism? No, it is not an isomorphism because it is not injective. but it is surjective. So for isomorphism, it needs to be both. So it is not an isomorphism. Now, what fourth case? So in fourth, we have a function given by this xy going to yx. Is this map an injective map? So again, for injectivity, come back to the definition here. We need to say that f of xy is equal to 0 if and only if xy is equal to 0. Now, what is f of xy? F of xy is y comma x. It basically interchanges the places of x and y. All right. Uh, so if x of x comma y is 0, that means y comma x is a 0 vector. Right?
I
So
think injective.
yeah, it is injective, right? Because y comma x is equal to 0, that means y is 0 and x is 0. Right? So that is the unique solution we get here. So it is an injective. Now, is it a surjective map as well? So,
Yes, sir.
for example, yeah, it is an surjective map. For example, what will be the image of 2 comma 3? What will be the pre-image of 2 comma
3 comma 2.
3? Right.
3,
It will be 3
2.
comma. Right. So it is. So for any element here, for any y comma x or x comma y or a comma b, what will be the pre-image of it? It would be just
Reverse of it.
yeah, b comma.
Opposite.
Right. Right. So it is a surjective map. So it is an injective map. It is a surjective map. So it is an isomorphism as well. All right. So yeah. So these were the things that we discussed last week. Now let us start with discussing today's objective. Today's prime objective is to associate a matrix to a linear transformation. All right. Now, once we do that, so for that, we need to talk about ordered basis. Okay. Ordered basis of a vector space. And once we have associated a matrix to a linear transformation, uh, we can we will talk about kernel in terms of null space and also range of a linear transformation. And after associating a matrix, we can translate the theorem of rank-nullity for a linear transformation as well. So uh, we will also talk about rank-nullity theorem for a linear transform. Okay, so this is today's objectives. So let me start with an example. So think of this function uh, f from R2 to R2. All right. So this function is given by f of xy is equal to 5x comma x plus 5. All right. So first, is it a linear map?
Yes,
So how
sir.
to check that? Yeah, how to check that? So we start with two vectors, x1, y1, and a scalar alpha, another vector to be this, and you calculate what is going to be value of this and what will be the individual value, individual sum, right? So this. Now it is for you to check that both are going to be same. So that is a linear map. All right. So can yeah, let's do this. So you guys let me know, tell me what is going to be the first one. So what is going to be this value? You do it on your notebook and let me know. Now, what will be the y coordinate? All right. And if you do it individually, then also you will obtain the same thing. Is it fine?
Yes, sir.
Okay. So now, so it is a linear map. Okay, let's skip this step. We have seen that. Now this function f of x, y going to 5x and x plus 5. Now you can write this function as a matrix multiplication as well. So if you guys remember that I started the discussion of linear transformation from an example of a matrix multiplication, right? So this is the kind of a reverse of it. All right. So for example, if you consider this matrix, which is 5, 0, 1, 1, okay, and you multiply f a with this vector xy, then what will you get? What will you get?
The same thing, 5x comma x plus y.
Right? You will get the same vector. So uh, there has to be some way to assign this linear function a matrix. All right. And now how do we get these coefficients of the matrix? Right? There has to be some way. So there has to be some relation between uh, this linear function and the coefficient of this matrix. So if you uh, so how do we get this coefficient? So for example, uh, so this is a map from R2 to R2. So if you consider the standard basis of R2, so what are the standard basis of R2?
1001.
Right. 1, 0, and 0, 1. These are the standard basis of R2. So you if you apply, so what is the value of 0, 1, 0 under the function f? Use this formula. So it is 5 times x, which is going to be 5 times 1 because x is 1. So it is 5. And now what is going to be the y coordinate? 1. Right? Now 5 comma 1. So
How is the
5
y
comma 1.
coordinate 1?
Yeah. So you apply 1 comma 0 here. So this is the function of this is the formula that I'm using. So if you place x equal to 1 and y equal to 0, what will you get?
Y is equal to 0 in the second one, right? X plus y.
Yeah, x plus y. So what is x?
Yeah, okay, so it'll be
X is
1, right?
1.
Yeah, yeah.
So it is 0. So
Okay, like
1
that,
plus
okay.
0, it is 1. Right?
Okay, okay. Yeah.
So now, and what is f of 0 comma 1?
0 comma 1, right?
Yes, it is 0 comma 1. Right? Now, Now, because 1 comma 0, 0 comma 1 are the basis of R2. So you can express any vector of R2 with respect to these two basis vector, right? Now, if I want to express 5 comma 1 with respect to the standard basis, what will be the coefficients? So I want you to tell me the coefficients if I express 5 comma 1 in terms of standard basis. So it is 5 times 1 comma 0, right? And 1 times 0
1
comma
time 0.
1, right? What about the second vector?
Yes, sir.
What about the second vector? What about this vector?
0 times
0 comma
1
1.
comma 0
Yes,
plus 1 times 0 comma 1.
right. All right. So now you can notice here that yeah. So notice that these coordinates are not anything. They are related. They are in particular the expression of 1 comma 0, the standard basis with respect to the images of the standard basis with respect to the standard basis, right? So they are the coefficients of the entries of the matrix is same as the coefficient of these images of the standard basis with respect to the standard basis. Make sense? Right? So for example, this 5 is this, 1 is here, this 0 is here, and this 1 is here. Right? So in particular, if you express your 2 cross 2 matrix in this way, A11, A12, A21, A22, right? Which means that A11 means first column, first row entry, right? Which is this one. A12 means what? First row, second column, which is 0. Similarly, A21 is second row, first column. And A22 means second row, second row, second column, right? So if you keep that in mind, yeah, yeah. So this is how I express a general matrix of 2 cross 2. Okay. This you might know already, right? Now, if I, so what are these standard bases? So these standard bases, I can name them to be E1, E2, right? And these are the standard bases of R2. But in my case, R2 is the domain also and codomain also. So standard basis of domain and standard basis, I have chosen standard basis of R2 in codomain also, right? So it is also E1 and E2. E1 and E2. So expressing f of E1. So I can also think of it as that I am expressing f of E1 with respect to 5 times E1 plus 1 times E2. Similarly, uh, I'm expressing E2 with 0 times E1 and 1 times E2, right? Now, this one and this one. So in order to name this coefficient, I will use these two indices, okay, 1 and 1. So this is going to be A11. All right. This is going to be A11. This is going to be A21 because second basis vector expressing the uh, first basis vector of the domain, right? This is going to be A. This is going to be what? This is the second
Two,
A1.
one.
basis vector of, yes, it is going to be 1, 2, right? And this is going to be A, 2, 2, because I'm expressing second vector of domain with respect to the second vector of codomain. So it is going to be 2, 2. And now these coefficients correspond to a matrix which
The
is
transpose, right?
not the not the it is the exact matrix AF. Okay, because what is A11? A11 is 5. What is A21? A21 is 1. What is A12? A12 is 0. A22 is 1. So
Okay, okay.
it is nothing but A. So you get the same matrix, right? So what I have done, so I have done these, I followed these 3 steps. First step is there is uh, I chose a basis of domain. Okay, let me call that beta, which is E1, E2. I chose a basis of codomain E1, E2, which is again the standard basis. Then second step is I expressed E1 with respect to E1 some coefficient A11 plus A, uh, A21,
2, 1.
E2. And similarly, this, right?
It's
And these
A1, 2, right?
coefficients,
So TE2.
uh, sorry, yeah, correct. Thank you. And these coefficients correspond to a matrix to me, which is this. All right. So I followed these 3 steps in this previous example to obtain, yeah. So I followed these 3 steps in this example to obtain a matrix corresponding to a linear. Okay. So first one is I fix a basis of domain. I fix a basis of codomain. I express the first set of basis. I express the set of basis of domain with respect to the basis of codomain, and I number the coefficients. This numbering, this indexing of coefficient is important because that's how you're going to uh, write the matrix. Okay. In simple terms, if you want to get in simple terms, so what is actually is happening is that you can think of that A is nothing but each column, each column of A is basically the image of TE1, right? Column of A is image of TE1 and TE2, right? That's what it is. Make sense?
Yes.
Right? So, so how to obtain A? You just need to find out the columns of A. And how to obtain the column? You can just, columns are nothing but expressing uh, basis, chosen basis with respect to the chosen basis of codomain. Okay. So let's do one more example. Uh, so let's take the same function f from R2 to R2, but now choose a different set of bases. Okay, of codomain, uh, let's take and domain, right? So function is nothing but 5x plus comma x plus 5. Now instead of choosing, so codomain, my domain is R2. Let me choose this set of bases, which is not a standard one, 1 0 comma 1 1. All right. And for codomain, let's stick to uh, standard basis. All right. So Now I want to express. So now this is my beta and this is my gamma. So beta and gamma, nothing but I'm just calling beta to be the set of basis for domain and gamma to be the set of basis for codomain. Okay. So don't worry about that. So now let me express my my function with respect to these set of bases. And then you will realize that you will get a different matrix. Correct? So let's do that. So how do we correspond a matrix? First, you just need to first we have chosen a basis. That is done. Now second step is to express basis of domain with respect to the basis of codomain. Now let's do that. So express basis of domain. So t of 1 comma 0. Now what is t of 1 comma 0? T of 1 comma 0 is 5 comma
1 comma 0. It's 5 comma 0. 1.
is 5 comma 1, right?
Yes, yes.
You just
Yeah.
right. Now you express 5 comma 1 with respect to the basis of codomain. So now basis of codomain are the standard ones. So it will just be the same. So it is 5 times 1 comma 0 and 1 times 0 comma 1. All right. Now expressing 0 comma 1. Now what is t of 0 comma 1? T of 0 comma 1 is
0, 1.
right. Now express it with respect. Sorry. Okay. Uh, now what is the other basis of domain? Other
1
basis of
comma 1,
domain is
right?
1 comma 1. So yeah. So I will express 1 comma 1 with respect to the basis of codomain. Now what is 1 comma 1? What is the image of 1 comma?
5
comma
comma
2.
2.
5 comma 2. Right? It is 5 comma 2. So now what is how do we express 5 comma 2 with respect to this codomain, standard basis of codomain? It is 1 times 5 times this and 2 times this. Now what is the matrix corresponding to this? Third step. What is AF?
5 5 1 2.
Right. So it is yeah. So first column is T f of E1. Second column is f of E2, which is going to be first column is 5 comma 5 1. Second column is 5 2. Right. So this is what the matrix is gonna look like. Right. So changing basis changes the matrix also. So what we have noticed here, we have noticed this fact. So basis determine the linear transformation or the matrix of the linear transformation. Determine the matrix of the linear transformation. All right. So it is important to know what basis you are starting with. Okay. And there is one more thing. The order of the basis. The order of the basis is also important. Important to fix. Okay. For example, if you take in this example, let's say in the previous example or even in this example, if you change the order of beta, what do I mean by changing the order? That means if I, let's say if I change the order of the codomain, right? If I change my basis to this order, 0 comma 1 and 1 comma 0, right? So if I change it to this, then my expression will also change. The corresponding matrix will also change. It will be different. So for example, these two entries will come first and these two entries will come second. So in other words, it will become uh, the first row will be the second row and the second row will be the first row. Right. So So the order is also important. In which order you are starting with, you are fixing your basis, right? So that's why that is what called the ordered basis. So you need to, whenever you fix a basis, you fix an ordered basis, and with respect to those ordered bases, we express a matrix. Does it make sense? Is it all right? So for example, if you take gamma prime, so this matrix is expressed with respect to beta and gamma. Now, if you express a matrix with respect to beta and gamma prime, then what will you get? You will get 1, 2, 5, 5, 5. This what will be your matrix. Make sense? Is it fine?
Sir,
Yeah, good. So order of the basis. So in which order you are taking? This is the first one, this is the second one, this is the first one, this is the second one. That also matters. Okay, so in order to express matrix linear transformation in terms of matrix. All right. So now let me write down in generality how does it look like. Uh, so for a linear transformation from B to W, let beta denote the basis of uh, the unordered basis of vector space B, and gamma, which is W1 up to Wm, be an ordered basis of W, then F, uh, then I can express each of the vector of domain with respect to the ordered basis of W, which is gamma, and the coefficients are going to be Ji of Wj. J is varying from 1 to m, right? Or let me use, so let me say Pji, Iji. All right. So where J is varying from 1 to n, right? And these coefficients correspond to a matrix which is nothing but whose columns are nothing but the images of the bases, which is V1, f of V1, f of V2, up to f of Vn. Or if I expand these columns, so you will get a a no. So you will get a11, a21 up to am1. Similarly, a21, sorry, a12, a22, am2, and so on. A1n, a2n, amn. All right. So you will get this. So uh, so we need to fix. So we need to fix the ordered basis of V and W. Once you have that, you need to express ordered basis of domain with respect to the ordered basis of codomain. And once you do that, you will get the columns of A. So columns of A are nothing but the coefficients expressing uh, image of. So basically, ith column of A is nothing but the image of ith basis of domain. in terms of the basis of codomain, right? So this is how you get the matrix. Okay. So is this all clear to all of you?
Yes, sir.
Good. So we will do one more example. We have already done two examples on the same function, and we have seen that the basis, fixing basis is important. The ordering of basis is important. If you change the order, you will get a different matrix, and so on. And we have seen that how to associate a matrix to a linear transformation. So that part is complete. Now, because of this, that given a linear transformation, you can associate a matrix to it. In particular, we have this theorem or result. You would say that beta, which is nothing but b1 up to bn, b ordered basis of b, and gamma, which is nothing but w1 to wm, the ordered basis of w, then any linear transformation, then any linear transformation from v to w correspond to a matrix. Okay, a matrix in m cross n. Okay, and the matrix you obtain by this one. And given a matrix in m cross n, there is a linear transformation that we have seen in the previous sessions, how to correspond a linear transformation from a matrix multiplication. So that was the motivation of one of the motivation of defining linear transformation. So given a linear transformation, one can associate a matrix. One can associate a matrix, and given a matrix, one can associate a linear transformation. Okay, so these two sets are equivalent. So whenever we will be talking about a linear transformation, there will be a matrix associated to it. So we will be working with that matrix. So if I want to find out, uh, yeah, so this isomorphism is important between, yeah, this isomorphism is important uh, between linear transformations and uh, in particular, this is a bijection. So this bijection is important because it associates a matrix to us, and we are already familiar with operations on matrix. Like there is a row reduce operation, row reduce, row reduction. There is an echelon form. We know how to find out the pivot element of that non-pivot element, dependent variables, independent variables, rank of a matrix. Okay, so all that thing can be translated back into the linear transformation and find out the properties, and we can find out the properties of linear transformation using the operation we already know on matrices. Okay, so this bijection becomes important in that sense, right? So we will see that now. Yeah, so this is important result. So let me keep it there, and let me start with defining what is kernel. Okay, so we have seen. Uh, so let me start with recalling this map. So in the beginning of this today's session, we were discussing this map between R2 and R, which was given by f of xy equal to x. All right, f of xy equal to x. So in that case, we notice that it is not an injective map. Okay, it was not an injective map. Why? Because if you take uh, 0, comma 3, image of this is again going to be 0, right? So there is a non-zero element whose image is 0. That's why it is not injective. Even if you can take any element at this, you can take any number at the y coordinate as long as you have 0 in the first coordinate, right? You can take any arbitrary real number in the second coordinate as long as you have the first coordinate to be 0. So its image will always going to be 0. Okay, that makes sense, right? So now, so what to be, so these set of elements whose image is 0. So in particular, vectors in R2 for this function whose image is 0. This defines a set. In particular, it defines a subspace. It defines a subspace of R2 in our case because the domain is R2, right? And we call this subspace to be the kernel of the linear transformation F. All right. So in this case, in our example, it is set of all xy in R2 whose image is a 0 vector. And we know what are these vectors? These are precisely 0, y. Here y is in R in our case. Okay. So yeah. So now let me write down the formal definition. So let F be a linear transformation from a vector space V to W. Then kernel of F is set of all vectors in V such that f of V is equal to 0. Is a 0 vector in W. All right. So one example you have already seen. Now let me take another example of the previous function that we were discussing. So the function was in R2 to R2. The function was given as
Sir, a small question. Actually, I've just now
right.
joined. So, is this week 6 or week 5?
Week 6.
Week 6. Okay.
Right. So this is what you express. F of xy is equal to 5x comma x plus y. Right. Now what is the kernel of this? So kernel of this is precisely the set of all vectors whose image is equal to 0, comma 0. So that means we get a homogeneous system of linear equation which is 5x equal to 0 and x plus y is equal to 0. And they both implies that x is equal to 0 and y is equal to 0. That means the kernel of this F is a unique singleton set. Is a singleton set. All right. This is fine. Is this fine with everyone?
Yes, sir.
Yes, sir.
Good. Now uh, we have associated matrix to a linear transformation. Okay, in our discussion here. Okay, and how to do that we already know that. So now this is a fact that the kernel of a function linear transformation So let me write down. Let F via linear transformation from B to W, then and beta, which is V1 to Vn, the basis of B, and gamma, which is W1 to Wm, the basis of W. Then kernel of F is same as the null space of A. Okay. So where AF is the matrix that we associated with F with respect to the basis beta of domain and gamma of codomain. All right. So for example, in this previous example itself, uh, yeah. So what is the associated matrix to this? The associated matrix to this was 5011, right? With respect to the standard basis, I'm taking standard basis. With respect to the standard basis, the associated matrix was 5011. All right. Now, if you apply row reduction to this matrix, okay, if you apply row reduction, now we need to find out the null space of this matrix. It is equivalent to finding out the null space of this matrix, which is again same as thinking that it is a solution of this set, right? So, which is again boils down to the fact that solving these homogeneous system of linear equation. And how do we solve this system of linear equation? We solve and find out that it has a unique solution. So either finding out kernel of a function linear transformation or finding out null space of the corresponding matrix is same. Okay, so they are equivalent under this bijection that we saw. Okay, so kernel of f is same as finding out the null space of this, and we know that finding out null space is a easier task. Okay, because you have a matrix, you can apply a row reduction, you can apply row operations over it, and you can obtain the row reduced echelon form. And once you obtain the row reduced echelon form, you can find out the dependent vectors, dependent variables, independent variables, and you can express your dependent variables with respect to the independent variables, and you can get the null space, right? So this is easier. This correspondence makes it easier. So we will see an example at the end of kernel and this thing, kernel and null space. So now let me talk about the, yeah. And there is one more fact about kernel. Let me write down some trivial facts about kernel and null space. So let's take this example again. Uh, Consider this function from B to W such that f of B is a zero vector. So these functions are called zero functions, zero maps. All right. Now, what is the kernel of this function? Now, what's the definition of kernel? Kernel definition is set of all B in kept set of all vectors B in B such that f of B is equal to 0. Now, if your function itself is a 0 map, then every element of every vector of B is going to be in kernel, right?
Right.
So, what will be the kernel then?
V.
Yes, it will be the whole space B. So, for an example, let me take a simpler example in terms of R2 and R. So, again, the function is a 0 map. Now, if you take any vector 3, 3, it will be 0. If you take any other vector 1, 2, what will be the image of this?
0.
0. So, if you take any vector, in particular, if you take the basis 1, 0, it will be 0. And if you take the images of the basis, it will be 0. So, any combination of them is again going to be 0. So, what is the kernel of this is going to be the uh, whole space, whole domain, which is R2. All right. So in this case, I'm talking about general vector spaces, so it is V. Now, what about the identity map? So it is a map from R2 to R2. It is called the identity map. Now, what is the kernel of the identity map?
R2.
Why? What is the image of 1, 1 under the identity map? Okay, so let me recall what is the identity map. So identity map maps xy to xy. Okay, this is what identity map. It just maps that element to uh, itself. Okay, so now what is the kernel of
It's
identity
a
map? Element type?
singleton set 0, 0.
Exactly, correct. Right,
Yes.
right. Now it makes sense, right? Now, um, yeah. So whenever we have identity map is an isomorphism. All right. Now let's take another example from R2 to R2, which is the orient rotation map, which we have already talked about, which says xy to yx. Right. Now, what is the kernel of this rotation map?
Again, it's singleton set 0, 0.
Right. Why?
X and Y will
Your
be
answer is
0.
correct. Yeah, x and y will be 0. There is another thing to notice that it is an isomorphism. We have earlier noticed that it is an isomorphism, right? Uh, so for isomorphism also, we are getting a singleton set to be, we are getting the kernel to be the singleton 0, 0, right? Or in other words, if I generalize this statement, then we have this that for isomorphism between B and W, F, then the kernel of F is going to be singleton 0 vector. All right. And yes. And there is one more fact. Whenever we have injective maps, right? Okay, so let me take another example. Uh, we have already discussed this example from R to R2, T going to T comma 2T. So we have seen that this is an injective map, right? But now what is the kernel of this?
That is also 0, comma 0, right?
Just zero. It is the
Okay, yeah, yeah.
domain is R only. Domain is
Ah.
R only. So it is a zero, right? So for injective maps also, we have kernel to be singleton zero or zero vector, right? So let's. So this is a fact that f is injective. It is same as saying that kernel of f is zero. Injective linear transmission if and only if kernel of f is singleton zero.
So again, we're proving that kernel is injectivity, right?
Yeah, we can prove injectivity by using this kernel.
Okay,
Right?
okay.
And we have also seen that kernel of a function is same as the null space of the corresponding matrix. Right. So let me also write it down here that kernel of f is same as is equal to the null space of the corresponding matrix. So kernel of f is zero. That means a linear transformation is injective. It is same as saying that corresponding matrix has null space to be trivial. Because from these two facts combined, we get f is injective linear transformation if and only if null space of AF is a singleton generated by zero vector. All right.
So
All
we
right.
will express the null space in the dimension of the domain or codomain. In the previous example, kernel, you told it is zero, right? Just below.
Yes. Below this, right.
Yeah.
This example,
Yeah, in this
this one.
example. Yeah, kernel we
Hmm.
will express in the in R here, right? Not in R2.
Yeah, kernel is always a subspace of R of the domain. That's what I write over here. Uh, it's a subspace of R2 in this case because the domain was R. So let me write it down. Yeah, here. So let me write it down. Thanks for pointing it out. So it is a subspace of V. Right.
Okay, thank you.
And uh, we know that dimension of null space is nullity, right? So of kernel, dimension of kernel F is nothing but the dimension of null space, which is nullity, nullity of A, right? So this is another fact. All right. So uh, for example, this F, the dimension of kernel is zero. In this rotation map, the dimension is again zero. In this identity map, it is zero. But in this zero map, it is dimension of V. Dimension of kernel is equal to dimension of V. Right? All right. So now let's talk about the image of a function or range of a linear transform. So image of F, I will write it in shorthand with IMF to be the set of all vectors in W because it is an image, so it will sit inside W. So it is set of all vectors in W, such that W is image of some vector in V, and it is n subspace of W. All right. So first thing, that image is a subspace of W, right? Now we have noticed while defining the bijection between the linear transforms and matrices, we have, or in other words, while converting, we have seen that. Let me go back when I was talking about this. So we have fixed the basis of B and fixed the basis of W, W1 to Wn, and we have expressed each of the vector basis vector with respect to the basis vectors of the codomain, right? And in particular, and the matrix associated with that is nothing but the columns. These columns are nothing but these entities coming from expressing each vi with respect to wi's, each vj with respect to wi. These columns are nothing but the coefficients of these expressions, right? And we obtain this column. So in other words, uh, if I have any vector v, okay, if I take any vector v in V, so because V1 up to Vn are basis of, they are the basis vectors of V. So we can express V with respect to the basis vectors. Let's say A, let's say V1, V1, Bn, Vn. This is the expression, right? Now applying your linear map F over this V, because it is linear map, you can, it distributes, okay? So it will be F of V1 plus Bn, Vn. Now, which is further, because it is linear map, so you can take each addition out. So it will be just nothing but V1 plus F V2, so on, F of Vn. And scalar multiplication also comes out, right? Because of the linear property. So F of V1 plus V2, F V2, so on, F Vn. Sorry. All right. So let me take this other way, somewhere else. Right. So let beta, so let V1 up to Vn be basis of V, and W1 to Wn be basis of W, right? So we can express this, and yeah. So in other words, I can, now let me write it down here neatly. So f of V can be expressed as f of V1, V2 of f of V2 times Vn f of Vn. In other words, f of V belongs to the belongs to the span of these vectors. All right, it belongs to the span of these vectors. Now, what is these vectors? These vectors are nothing but the columns of AF, right? So, in other words, it belongs to the column space of AF. So what we have shown is that image of F is sits inside the column space of AF, and the other thing is true. In particular, the image of F is same as the column space of F here, right? So this is a proof of this fact that image of F is nothing but the column space of. Is this clear to everyone?
Please explain with one example.
Yeah, I will do that. All right. So, for example, let's take the example that we did. So F is a map from R2 to R2. We have xy of F going to 5x plus x plus y, right? And what is the associated matrix? AF was 5, 0, 1, 1. Now, what are the column space? Column space of AF is, now what are the columns? C1 is 5, 1, C2 is 0, 1, right? Now, what is the column space of AF? Column space of AF is any combination of C1 and C2, right? So it is 5, 1, 0, 1. A span of 5, 1, 0, 1. These two vectors, right? Now, what is the image? Image of F. Now, image of F is 5x plus 5x comma x plus 5. Image of F is precisely 5x comma x plus 5. X and y are in R. Now, this can be expressed as 5 x plus 0 comma 0 comma y. All right. Now you can take 5 out as well. You will get 1 comma 1 plus 0 comma 1. Sorry, what did I? You can take x out. You will get 5 comma 1 and y this. Right. So in other words, image of F is generated by 5 comma 1 and 0 comma 1. So these two things are same. Make sense?
Yes.
Good. So what we have shown that image of F is nothing but the column of F, column of AF. Image of F is nothing but column of AF. So if I want to know what is the image of F, I just need to find out the matrix A. Okay. So for image of F, what do we need to do? We just need to start with function F. We need to find out its corresponding AF. And once I know the corresponding AF, I know the column space of AF, right? And that column space is going to be the image of F. That's all. Okay. So now, to find image of F, this is how we do, right? Now, let me take some more examples. So for example, zero function that I defined to be zero function from vector space B to W, any vector B going to zero, right? So what is the image of F? What is the image of this function, zero function?
0.
Right. It is zero, just zero vector. Okay. Zero W means it is a zero vector in W. No, and I don't want to confuse you, so I'm just writing this sub-index W, subscript W. Okay. Another example, the identity map B to W, which takes, sorry, identity map between R3 to R3. It takes XYZ to XYZ. Now, what is the image of this identity map?
R3.
Right. It is R3 itself. Now, let me.
So why is it R3?
It is R3 because it is the identity map. So every you take.
Okay, yeah. Okay, is it? Okay, yeah, got it.
You have you got it? So okay.
Yeah,
So
I
if
got
you
it.
want, we can. Yeah. So what is the if I want to express this function? So what is the matrix corresponding to this function? Let's write
1 0
that.
0 1 0 0 0 1.
Right. This is the matrix, the identity matrix.
Yeah.
And now, what is the column space of this?
1
Column
0
space.
0 1 0.
It is going to be whole of R, right?
Yeah.
So that's the image.
Okay, got it.
Make sense? Right. Now let's take another example, which we did earlier as well. Function f from R to R3 defined to be t going to t, 2t, 3t, right? So now, in this case, what is the image of f? So let's do the matrix method. First, what is the matrix A? Matrix A is going to be, it is going to be a matrix of, I just need to express T. So there is only one basis, one, f of 1. F of 1 is 1, 2, 3, right? Now, how do I express 1, 2, 3 with respect to the standard basis of R3? It is 1 times 1, 0, 0, 2 times 0, 1, 1, 0, 1, 0, and 3 times 0, 0, 1, right? Now, f of 1 is going to be the column. The coefficients are going to be the column. So it is 1, 2, 3. So this is my AF. Is this clear? How do I obtain AF from this for this function?
But why is it 1 2 3? The 0 is not counted. Or
Okay, let me do it once again.
that part I understood, but how is it 1
So what is the standard basis of R?
0? R is, I think it's only 0, right? 0
No,
or
it's
1. I think it's 1.
1, right? It is 1.
Okay.
So standard basis of this is 1, just real number 1. And standard basis of R3 is
1 0 0 0 1 0 0 0 1.
right.
Yeah.
Now I need to express basis of domain with respect to the basis of codomain, right?
Okay, that I
So
understood.
what is f of 1? F of 1 is 1, 2,
1
3.
3. Okay.
Now I need to express 1, 2, 3 with respect to the standard basis of R3.
Yeah, you have to
How do I
multiply.
do that?
Here you express
Wait.
codomain with respect to domain, right?
Yes,
1,
yes.
2,
No. I'm expressing domain with respect to codomain. I'm always expressing domain with respect to codomain. What is codomain here? R3. What is
R.
domain here? R.
R.
So I'm expressing basis of domain, images of basis of domain with respect to the basis of codomain.
1.
Right? So how do I?
Yeah.
So how do I express 1, 2, 3 with respect to the basis of codomain? It is
Yeah.
complete this. Can you guys complete this?
1, 0.
0, 1, 0 plus it's 2 into 0, 1, 0
Right.
plus
3
3
into
into 0,
0,
0, 1.
0.
Right.
Yeah.
So now what is the corresponding matrix? Corresponding matrix is going to be the
1,
f
2.
of 1 will become the column.
Okay.
So the coefficients become the entries of that column. So it is 1, 2, 3. Right?
The coefficients become the entries of the. Oh, okay. Okay. Oh, okay. 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 Now I get it. Yeah. Sorry.
Right? Because there is
Yeah.
only
Yeah.
one basis, that's why you might be getting confused.
Yeah.
There is
Yeah.
only one basis of domain. So you just have one column, right? So it is 1, 2,
Yeah.
3. Now, now what is the column space of this AF? Now you apply the row reduce. You first obtain the row reduce echelon form. So what will be the row reduce echelon form of this matrix? First we R2 minus 2R1,
2 R1.
right?
Okay. Yeah.
R3 minus
3 R1.
3R1. What will we get?
1, 1, 1.
No,
1, 0, 0.
1,
Sorry.
0.
Sorry. Uh-huh.
Right. Now what is the column space of AF? 1, 0, 0.
1, 0,
It is
0.
just 1, 0, 0. That's the generating. That is the basis, and this is the generator. So column space of AF is this. Right? It
Okay.
is just so that's the image of F. Okay?
Okay. Okay. Yeah. Yeah. But why are we reducing it?
Yeah, in order to find out the image, that is one. It is a row reduced echelon form tells you. It gives you the basis also. So this is another basis. You can just write 1, 2, 3 also. That is. I
Okay.
just
Oh, this
want to
is
make sure
another
that
basis.
you understand.
Okay.
1, 2, 3
Huh.
is also another basis.
Okay.
Reducing just to tell you that there is only one vector. There is generate 50, right?
Yeah. Yeah.
Yeah. This method of row reducing is important if in case you have multiple columns, if you have a bigger matrix, then it makes sense. In this case, it doesn't make sense, but it's fine. All right. So yeah. So now uh, the column space of this is this, or image of the function is what is the dimension of this image, or what is the dimension of this? What is the dimension of image of F?
Is it 1? Because 1 non-zero row.
Yes, it's one only,
Okay.
right? Because there is only one basis generating that. There is only one non-zero row in the row reduced echelon form. So dimension of this is 1. So
If the same example is R2 to R3, then how it will be?
in the same
2
example
comma
from
some
R2
other
to R3,
variable, right? If it's R2 to R3, it'll be T comma Z, 3 comma Y, another variable, right?
there will be something S comma T
Some
like
other variable, yeah.
and then you need to express it with respect to that. Yeah. So
Where we will take 1 comma 0 and 0 comma 1 like that.
there will be one more column. There will be one more column. In that case, okay, let's do that. So let's take F2, define F2 to be this way. F2, a map from R2 to R3, take X comma Y, and just map X, 2X, 3X, right? And now what is the associated matrix to it? So first we need to, so I'm taking standard basis in both cases. Now what is the standard basis of R2?
1 comma 0 and 0 comma 1.
Right. Now you apply function over it. What do we get? F2 of 1 comma 0 is
1, 2, 3.
2, 3.
1, 2, 3. And what is F2 of 0 comma 1?
0, 0, 0.
0, 0, 0.
0, 0, 0. Right. Now express each of this with respect to the standard basis of R. It is going to be 1 with respect to 1, 0, 0, 1,
2.
2, and then 3. Right. What about this second vector?
0, 0.
0.
All coefficients will be 0. Right.
Yes.
So E1, E2, E3, right? Now, what is the matrix corresponding to this columns? Each column is going to be the coefficient of this thing. So first column is F2 of 1, 0. Second column is F2 of 0, 1. Right? Now, what is the first column?
2, 3, and 0, 0, 0.
0, 0, 0. Right? Now, what is the low reduced Echelon form of this?
1, 0, 0, 0, 0, 0.
Right?
The dimension
Now,
is
what is
1.
the dimension is 1, and there's only uh, uh,
1
basis. You
base.
can also find out the basis. First basis, which is 1, 2, 3, is the basis, right, of the
Yeah.
image. So, as we have, as I said, that dimension of uh, kernel is because kernel is same as the null space of the matrix. Similarly, we have proven that image of the function f is same as the uh, uh,
Column.
column space of the matrix, right? So the dimension of the column space is equal to the dimension of the image, right? Now, what is the dimension of column space? What is dimension of column space of that? It is called the rank of the, right? Recall that. It is the rank of, it is rank or column rank of it, right? It is rank of it. So, in other words, rank of AF is same as the dimension of the image of F. Okay. Now, another thing is that if your function is surjective, if F is surjective linear transformation, then what will be the image of F?
The rank of AF.
It's the codomain.
Yeah, it will be the whole of Kodo, right? So if F is a function from V to W, then image of F is going to be the whole of codomain, which is W. So this is another fact. Uh, right. So yeah, now we have seen that rank of AF is same as the dimension of image, or as well as we have seen uh, that dimensionality of AF is equal to the kernel of F. Okay. So let us recall the rank nullity theorem for a matrix. So what was the rank nullity theorem?
Rank plus nullity is equal to the number of columns.
Yes, right. Rank nullity theorem, which says that rank of A plus nullity of A is equal to number of columns of A, right? So if my matrix, if my linear transformation, if F is a linear transformation from V to W, where dimension of V is n and dimension of W is n, and let this also assume that uh, V1 up to Vn denote the basis of V, and W1 up to Wm denote the basis of W. When we know that the matrix that we will get is going to be a matrix in M cross N, right? This we already know. It is going to be a matrix of M cross N. And we know that rank of AF is equal to the uh, rank of A is equal to the dimension of the image of F. And third, we know that nullity of AF is equal to the dimension of the kernel. Right? So by rank nullity theorem, if I apply rank nullity theorem for AF, what do I get? That dimension of kernel of F plus dimension of image of F is equal to number of columns. Now, what is the number of columns? Number of columns is n. Now, what was n? N was the dimension of
Dimension of
V.
V.
So it is equal to dimension of V. So this is the rank nullity theorem for a linear transformation, right? All right. So now let us do an example where I will discuss null space. I will discuss the uh, image, and I will also discuss, how to obtain this matrix as well. Okay, so let's do one example which will incorporate all the details that we have discussed. Now let's take your V to be R2 and W to be X, Y, Z in R3 such that X plus Y plus Z plus 2Z is equal to 0. So it is clearly a subspace in R3. All right. Now, uh, so is um, right. So now what are the so W is the subspace of R3. Now what are the bases of R3? So can you express? Can you find out the basis of R of sorry? Can you find out the basis of W using this equation? Basically, the generating set of W. We need to find out. We want to find out the generating set of W. So W is nothing but it is a plane sitting inside R3, which is where the plane is defined by this equation x plus y plus 2g is equal to 0, and this plane is passes through the origin. So it is a linear subspace of R3. Now, uh, what are the generating set of this W? Anyone? Like, how do we proceed?
Sir, x is equal to minus y minus 2z.
Exactly. So x is equal to minus y minus 2z. So that means if I replace x with this quantity, right, y, z, and if I express this, uh, if I try to separate variables y one term, one in one vector and z in one vector, what do I get? Minus y 0 plus minus 2z 0 z. Correct? Till this point it is fine. Now you take y out, minus 1 1 0. You take z out, minus 2 0 1. So in other words, W is generated by minus 1 0, minus 1 1 0, minus 2 0 1. Is this fine with everyone?
Yes, sir.
Good. So I will take this as my basis. So I will take this as my basis for codomain. And I will take standard basis for my domain. What are the standard bases of R2? It is 1, 0 and 0, 1.
1.
Right. Now let us
Sir,
associate matrix correspond.
sir, is there any other method to find the basis, sir, with this equation? From this point, like x is equal to minus y minus 2z. From there,
Right.
whether we can substitute 0 and 1 for y and z, and can we find the basis, sir?
Yeah, you can do that also.
Is that also okay?
So yeah. So the same method we discussed while discussing null space as well. You can take z to be t1. Sorry. Uh, y to be t1, z to be t2, and take t1 equal to 1, t2 equal to 0 in first case. Second case, t1 equal to 0, t2 equal to 1 for the second case. And then you will get set of vectors. So you will get the same basis if you do that. You will get the same basis. There won't be any change. You can do that as well. It is completely fine.
Okay, sir.
Yeah, this I find convenient to do
Whichever
because
is
it
easy.
is explicit. Yeah, this is like kind of explicit. You can just separate out the one variable one in one vector, other variable in the other vector, and then you take that variable out, and then the remaining is the you left with the basis vector. So this is kind of easier, convenient to do. Okay, so I have fixed codomain basis to be this and domain basis to be that, and now let me write down my function. So my linear transform f from V to W is uh, given by f of x comma y is equal to minus 3x minus 3y x plus y and x plus y. All right. So first task is to express the basis of domain with respect to the basis of codomain in order to get the matrix. So what is the basis of domain? Basis of domains are standard basis. 1, 0 and 0, 1. Okay. So let's start with 1, 0. Now what is 1, 0? What is the image of 1, 0? What is the image of 1, 0? Just plug in the value here and then you will calculate.
Minus 3, comma 0. I
Uh,
think. No,
minus
wait.
Minus
3,
3,
comma
1 and 1. 1, 1.
right.
1,
And what
1.
about
Sorry.
0, comma 1?
0, comma. No,
It
wait.
will be same.
How is it?
Minus 3,
Minus 3.
minus 3. So just
Oh,
place
yeah.
0 here and 1 here. Okay, so
Yeah,
it is
yeah.
minus 3 times 0. 3 times it is 0, 1, 0, 1, right? So we will
Yeah.
get 3, comma 1. Now we need to express minus 3, 1, 1 with respect to the basis of W. Okay, so minus 3, 1, 1 is equal to A times minus 1, 1, 0 plus B times minus 2, 0, 1. All right. Now you will get minus A minus 2B, A and B is equal to this. Now if you solve that, what will you get? You get a system of heterogeneous system of linear equation which has a solution, right? It has a unique solution. A equal to 1 and B equal to 1. Is that correct?
Yes, sir.
Good. So I can express this as 1 times minus 1, 0 plus 1 times minus 2, 0, 1. Same with this, right? So I get the coefficients as well. Now let me write down the matrix. So what is the matrix? Matrix is first column is going to be F10, second column is going to be 0, 1, right? Now what is the first column?
1, comma
What are
1.
the entries? 1, comma 1. What is the second column?
Again 1, comma 1.
1, comma 1. Right. Now, I want to find out the kernel of AF. I need to find out kernel of AF, first thing, and then image of it. Sorry, kernel of, I need to find out kernel of F and image of F.
Kernel
Now,
of
what
F
is
is
the kernel?
rank, right?
No, kernel of F is, kernel is a subspace. So it is null space of AF. Rank is the dimension of, no, rank is, it's not the rank. Uh, dimension of kernel is
Is
nullity of
nullity.
AF.
Is it
Yeah,
nullity? Yeah, okay.
it's not nullity. Yeah, it is nullity, but the dimension is nullity. Kernel of F is null space of AF. Okay,
Okay.
because it's a subspace. It's not a number. It is a subspace. So, uh, yeah. Now, in order to find out the kernel, first we do reduce this matrix.
Sir, I have a doubt, sir.
What is the? Yeah, please.
Sir, could you please explain this, the f of x comma by y equal to minus 3x minus 3y, that steps. Why we are adding it, sir?
F. Why are we adding?
These two bases. We are adding the bases, sir.
Yeah, we are adding because look at the image. The image of the first vector of domain. It is 1, 0. What is the image of 1, 0? It is minus 3, 1, 1. Now I want to express minus 3, 1, 1 with respect to the basis of codomain. Right? So this is how I find out. So how do I explain? How do I find out the basis? How do I express this vector? It needs to be some linear combination of
Sir,
these
I'm
two vectors.
asking the previous step, sir.
Uh,
F of
okay.
x comma y
This one,
equal
this
to,
one,
that is okay, sir. The next steps.
this one.
Yes, sir.
This is the definition of function. I'm giving this definition. This is a linear. I'm defining this linear transformation like this.
It is it is given in the problem, sir.
It is given. It is given in the problem. Right.
Okay.
It is
We
given
are
in the
not
problem.
adding
Right.
it, no? We are.
No. This formula for the function is given to us. This is part of the question.
Okay, sir. Okay.
Yeah. Okay.
Okay, sir.
Right. Now, what is the kernel of F? To find out the kernel of F, we row reduce this. After applying R2 minus R1, we get 1, 1, 0, 0. Right. This is the row reduced echelon form. Now, what is the null space of this? Null space of this is precisely
1 0 1 0. I think.
no. Okay.
Oh no
Null
no no.
space of this.
Image. Okay, that is the image. Sorry.
Yeah. So for
X
null
plus
space,
y
you
is
need to
equal to
solve this.
0.
So that means x is equal to
0
minus,
y.
and y is the independent variable. Right. So if you express the null space, it is going to be minus y, comma y in R, y in R. Right. This is the null space of A. Right. So in other words, you can take y out. It is just nothing but minus 1 comma 1, generated by minus 1. Now, what about the image of F? Image of F. Yeah.
1 0,
It'll
right?
be the column space, right? 1 0 1 0.
Yeah, it will be the column space. So it is,
1 comma
what is the
0.
first vector? First vector is 1, 1. Right. First vector is 1, 1. That's the first vector. But this 1, 1 column is, we need to express this 1, 1 column with respect to the basis of W. Right. So in particular, these 1, 1 column represents the coefficients of the vector which is going to span the image. So it is going to be 1 times the first vector, 1 times the second. So first vector was minus 1, 1, 0. Second vector was minus 2, 0, 1. So it is minus 3, 1, 1.
If
So
we are taking the column space, how it is 1, 1, it is 1, 0, right?
If we multiply 0, it becomes 0, right? 0 with the vectors.
yeah. So this is the pivot in the first column, right?
Yes,
If the
yes.
pivot is in the first column, we take the first column uh,
Okay,
of
okay.
the matrix of the order, right? That's how we do, right? So we have taken the first column of this thing, but we need to express this column with respect to the basis of W. So how do we express this multiplied with the first vector, first basis, this multiplied with the second basis. So this is how we do it, and this is the generator of this. So we have obtained the image also as well. And now, if you find out the dimension of kernel, dimension of image, and dimension of the domain. So dimension of the domain was 2 because we started with R2. Dimension of domain is 2. Dimension of kernel is 1 because it is generated by single element, single vector. It is 1. Dimension of image is also 1. So it is 1 plus 1 equal to 2. So rank nullity theorem is also verified. All right.
How did dimension of
More
image become 1?
because there is a one vector. There is only it is generated by one vector, right?
Oh yeah, the 1, 1. Okay, okay, okay.
Or no, not the 1, 1. This vector. This is the
Yeah,
generating vector of W.
huh.
1, 1 is not the generating vector of W. It is just it gives you the coefficient with respect to the basis. Or in other words, you can just look at the column space. So what is the column space of this? Column
1,
space is
1.
what is the rank of this matrix?
Oh,
Rank
okay,
of this
okay,
matrix
okay.
is 1,
Huh,
right?
okay.
It is all same. So uh, so this is also right. So next Monday we will do some more examples. And if you have any query about these topics that we discussed today, you can come up with those query next Monday. Okay, so next session is going to be next Monday. This week there will be live sessions, live revision sessions uh, on, I guess, on Wednesday and Thursday. Okay, and then there will be quiz on Sunday, and then there will be TA sessions as well. So, so quiz is going to be based on syllabus of week 1 to week 5, and I would like for you to use this week's revision sessions to make most out of that. Okay, Sanidhi will be taking those live sessions, these revision sessions. So all the best for the quiz. And next Monday we will be continuing with this week 6 syllabus, and I will talk about more of these examples. And if you have any questions about these rank, null, rank, and these kernel uh, and image of a linear transformation, we can discuss those doubts next Monday as well. Okay, and I will give more examples. So thank you. Thank you for attending and being this interactive to me. It helps a lot, and I will see you next Monday. And all the best for your quiz.
Thank you so much. Good night.
Thank you,
Yep.
sir.
Thanks. Good night.